Good morning. The projector is not supposed to be on. So you're all going to be guinea pigs this morning because I've rewritten this talk several times in the last week. And the truth is I'm still not actually that happy with it. And this morning when I woke up, at 6 a.m. or so East Coast time, which is my usual habit, I started working on it again, and I realized that I could either have something that approaches a coherent talk, or I could have a coherent set of slides, but I couldn't really have both at that point. And so you're going to get the talk, which is okay, because the way that I normally do slides anyway is just as cue cards for myself, and I have those up on my screen anyway. So my title is Slow but Steady, Achieving Real Security Within 2 Decades. And normally for a talk like this, one begins with motivation. One asks the question, why should one care about this topic? If there is anyone in this room who doesn't think that computer security is a continuing crisis, tune into the news at some point. I think that we're past the point where talks like this have to begin with a litany of problems. We all know what the problems are. And I'm here today to make a completely insane claim, which is that this is actually fixable. Not perfectly fixable, and there are lots of things that we're not going to be able to fix that I'll get into, like people very, very deliberately shooting themselves in the foot. But I think that we can probably close most of the major classes of security holes that hit people who are doing things correctly. I don't claim that we can achieve perfection. I'm not sure even what perfection means. But I think that we can get to the point where the crisis that we've been in since the 1980s, and I think it's been a continuing crisis that's just been building and getting worse and worse and worse since the 1980s, can finally be put behind us. And I'm going to cover a lot of territory today, and in a somewhat indirect way, but I assure you that underneath the apparently incoherent presentation I'm making, it's actually not that incoherent, there is a coherent message. And the message is that although there isn't a single silver bullet out there with which we can kill the security problem, there are a lot of silver bullets. And if we use all of them in combination strategically, we actually can fix this. It's not past our ability to fix. It's not stuff that is completely not understood. There's still a lot of research to be done. There's still a lot of practical work to be done on figuring out the engineering, but we can actually get past this. And the fact that it might take a lot of separate things in combination shouldn't be too surprising. There have been lots of things in human history that have been fixed this way, often very long-term intractable problems. I'll give an example of a long-term intractable problem that was fixed this way, which is public sanitation. Okay, so I've heard it's claimed, and I'm not sure that it's true, but I have to believe the people who claim it, that most of the increase in human lifespan between about 1800 and today is just because of improvements in sanitation. And human beings didn't have proper sanitation for, the 100 or couple 100,000 years that Homo sapiens was on the planet before, the mid-19th century. How did this happen? Did it happen because someone invented a single great advance? No, it was a lot of advances. First of all, there was the fact that the Industrial Revolution lowered manufacturing prices, which meant that lots of things like piping and pumping equipment and what have you was cheaper. Sewer systems were designed for the first time and implemented. Water distribution systems were designed and implemented. And then later on, people figured out that simply having a water distribution system wasn't enough, that they also needed water treatment systems. Indoor plumbing arrived because the Industrial Revolution lowered the cost of the things you needed for indoor plumbing. People put in indoor plumbing. A thing people don't think much about was the fact that the price of soap plunged, because in mass industrial manufacturing meant that soap was no longer something expensive, but something so cheap that even very poor people could afford to wash their hands after going to the bathroom. And bit by bit, piece by piece, this intractable problem that plagued human beings since the dawn of time vanished. And I'm probably leaving some bits out here, and I'm probably oversimplifying. Someone who actually is an expert on the sanitation problem watching this will probably be cringing, but that's okay, because we're discussing computer security today, and I'm just using it as an exemplar. So I'm claiming we don't have some single magic method that's going to fix everything, but a lot of methods put together and composed properly probably can. And I'd like to condition people's expectations here. It is really not possible to fix everything. For example, in the unlikely event that in a decade or two we have really, truly, completely secure operating systems, which we don't quite need in order to fix the problem. But let's say we did, there'll still be people running Windows XP somewhere. And you cannot stop someone from doing that. And we won't be able to convince them to upgrade, and they'll claim that it's just fine and they've never had any trouble over all these years, and what are we going to do? You also can't stop people from being fools in other ways. For example, you cannot stop someone from, of their own free will, deliberately deciding to wire all their money to a stranger in Africa who claims to be a prince. You can't. You could imagine all sorts of remediations you could undertake, but the fact is that unless you take away people's ability to freely transact with their own money, you can't stop them from doing really stupid things with their money. There are other things like this. Like you can't stop people from building malicious hardware. You can't stop manufacturers from selling people deliberately constructed malicious hardware. You can't stop manufacturers from including a telnet daemon that cannot be turned off on a web camera, along with a hard-coded password that's sitting there in firmware that cannot be updated. Not that this, of course, has happened recently, but you can't stop that. That if someone is going to take aim right at their foot and pull the trigger, we can't stop that. But the problem we've got right now isn't that people are deploying versions of the Illinois malicious processor. It isn't the fact, and most of you probably left your laptops in the safe in your hotel room when you went to dinner, not thinking too much about the fact that people could come in and bug your computer or otherwise backdoor it while you were out. It's not a big threat. The biggest threat we have right now is mass exploitation on a network scale. And we have the problem that individuals and organizations that do absolutely everything right with their security, that follow all the advice, that design their stuff reasonably well, they're still vulnerable. Okay? And they're still vulnerable because all the things they depend on, the operating systems, the libraries they're using, the software on their routers, everything, it's all filled with security flaws. No one needs to deliberately sabotage you. You don't need to be particularly stupid. You don't need to do anything that goes against advice. Your machine can be sitting there on the network, minding its own business, processing JPEG files being uploaded by your customers, when it turns out that there's a remote exploit in your JPEG library, and that's the end of you. And the problem is that everything is built on sand. In fact, it's worse than that. Everything is built on quicksand. And so what I'm arguing is we can fix that. We can't keep people from shooting themselves in the foot, but we can get it to the point where people who are not being stupid are okay. So I'm setting this as our modest, realistic goal. And of course, you're probably going to say that fixing security most of the time for people who are mostly doing things right is still crazy. I'm arguing it's not crazy. And so, I think we could actually manage that. We can't stop mass network denial of service attacks from bringing down hardware. I mean, it's difficult even in principle. But we can probably stop worms and botnets from taking over millions of machines to allow people to undertake huge denial of service attacks. I don't think we can stop the sabotaged hardware, but I don't think we need to for the most part. I think we can manage to do a lot of good even without that stuff. So the goal is simultaneously modest and insanely ambitious. And I know what you're going to ask now. What do I know that you don't know? And the answer I'm going to give you is that I don't know anything most of you don't know. There might be a few small things. You know, I might know a little bit more about the state these days of formal verification that some of you are not aware of, though I think that a lot of you are aware of it. And I might know a few other small tricks, but I don't think that I actually know much you don't know. What I do think, however, is that I may have, you know, have thought about this slightly differently than the way that other people have. And I'd like to direct your gaze at the things that you already know slightly differently. And I'd like to suggest that what we really need to do is systematize how we are applying the tools we already have and apply them very, very aggressively, which we have not been doing up until now. And so just another brief success story, this one actually in our field rather than, you know, something mid-19th century. You know, decades ago, we had an analog cell phone system in the United States, which was riddled with toll fraud. People, because the phones would send out their identification information in the clear over the radio. All someone had to do in order to be able to clone a phone and be able to engage in toll fraud was to listen in, grab the stuff off the air, and then they had everything that they needed in order to engage in toll fraud. And the carriers tried all sorts of patches and remediations that didn't get around the basic problem in order to solve this. And they basically didn't work. But then, quite naturally, people started turning over the system from the analog networks to the digital networks, and toll fraud vanished. It vanished completely. You know, a problem that had been intractable for years vanished. And why did it vanish? It vanished because the signals started being encrypted, or at least the important part from the point of view of the carrier. The carrier doesn't care about whether people are listening into your call, but they do care very, very deeply about whether or not other people can steal your credentials and start committing toll fraud against them. And by encrypting that part of the signal, the fraud ecosystem vanished. There were tens of thousands of people around the world probably employed full-time in committing fraud, okay? And suddenly they didn't have jobs. And so problems like this do not have to last forever. We can kill them. We can put a stake through their heart if we try. And another thing I'd like to point out is that we've been taking a strange view of computer science for some years. We all view computer science and everything we do as a very, very rapidly changing field in which there's enormous turnover and things tomorrow will be completely different from the way they are today. And this is not true anymore, and it hasn't been true in a while. Okay, so this device in my pocket runs Unix. And in fact, there are now, I think there's some crazy statistic, like 1/3 of the world's population. I probably have it off by a bit, but it doesn't matter. Like some crazy fraction of the world's population now have smartphones. And that implies that that fraction of the world's population now have what is more or less a 50-year-old operating system running in their pocket. Unix is about 50 years old. TCP/IP is about 40 years old. Well, Windows NT is about 20 years old. You know, SSH, you know, even in fact the SSH code that almost all of you are running is decades old. You know, GCC is decades old. Everything we use has, you know, a lot of our fundamental infrastructure, most of our fundamental infrastructure is not new, and it's not going anywhere. Okay, so maybe in 1980 there was an expectation that everything would be different in 15 minutes, but that's not the case anymore. Hardware is fleeting, but software seems to last forever at this point. Unix has lasted 50 years without slowing down, and it may last another 50 years. Hell, it is possible it might last another century. I'm not joking. It could be around for a very long time because the things that it does are things that are going to continue to need to be done for quite a long time. It's possible that even libpng or libjpeg might last another 50 years, okay? Everything around us is actually lasting much longer than we give ourselves credit for. We're no longer building stuff that lasts only a couple of years. A lot of the stuff that we're building may outlast our children, okay? So this means that we're living in a different world, we're no longer living in a world of one-off hacks. We're living in a world of engineering, okay? And unfortunately, though, software engineering up till this point has been much more about aspirations than about actual practical techniques. And people have, wanted software engineering to mean something for quite a long time. In the 1970s, there was all this talk about the software crisis. People started researching software engineering in a serious way, and they came up with a lot of methodologies. And I'm going to be very contemptuous of them, but I want to start by saying that I'm not actually contemptuous of the people that came up with them. I'm contemptuous only of the results they came up with. But hindsight is 20/20. People make mistakes. It's difficult when you're a pioneer to have the bird's eye view. So people tried things. One of the things they tried, for example, was they looked at how civil engineering and aerospace did things, and they noticed that if you're building an airplane, you don't start putting it together on the shop floor without any forethought. You build plans for it, right? And you build complete plans for it, and only then do you actually go out and construct it. The problem was that people did not understand that when you're building the plans for an airplane, it's an iterative process. There's a lot of creativity and thought, and you juggle things around halfway through. And that software is not like building an airplane in that the plans are the finished product. There is no distinction between a program in the end and the plan for constructing the program. They are the same thing. So people came up with these cargo cult methodologies, and the result of this was bad kinds of software engineering, like the waterfall methodology that's been popular in software engineering for a long time and has been something of a failure. There have been other kinds of failures in software engineering, like in the field of measurement. And by the way, I'm not contemptuous of measurement at all, but because measurement's a really, really useful thing. But for a long time, we were measuring stupid things, like cyclometric complexity. Many of those of you who are younger will never have heard of cyclometric complexity because it turns out to be useless. It doesn't actually help you fix anything. But at the time that it was invented, people were really, kind of interested in it. So what we need to do is we need to develop a real discipline of software engineering. And I'm arguing that many of the people in this room, even by being here today, are part of that. Okay? We need an engineering discipline that systematically addresses what we actually care about. And what we care about is eliminating bugs or assuring that they remain contained and cannot spread and cause problems throughout a larger system. And people worrying about programming in the large have finally been getting the hang of some of that. Test-driven development and things like that are far better than the older ways of thinking of testing systems. We're getting our hands around parts of this. But of course, testing only can take you so far because testing cannot prove the absence of bugs. And it turns out that security requires the absence of bugs. And we've all been trained, of course, to think you can't actually ever get rid of bugs, right? There's the old joke, every program can be shrunk by one line, and every program always has one more bug, so every program can be reduced to a one-line incorrect program. And we tell jokes like this among ourselves in the software community because we all know you can't get rid of bugs, right? Except you can get rid of bugs. You can't get rid of all bugs, but you can get rid of the important classes of bugs. And I find this to be what makes LangSec so interesting and promising. And I'm sure you were wondering when I was going to mention LangSec. And I'm going to avoid discussing LangSec in much detail. And the reason for that is that everyone in this room already knows all about LangSec. And there's no point in my describing back to you the work that you are already doing. And for those who are watching on the video, look up LangSec, read the papers. It's one of the most exciting things to have come up in the computer security field in a while. But I am going to discuss LangSec for a moment in the abstract. And I hope those of you who are responsible for coming up with the idea will forgive me for telling you back what you did and why it's so cool. So I think that the genius behind LangSec was to look strategically at a huge source of computer security issues, abstract out a common thread between all of these issues, which is shotgun parsers, and the fact that there was a giant mismatch between the language you thought you were recognizing and the language you were actually recognizing. And then not to try fiddling around the edges or coming up with remediations or finding better ways to build shotgun parsers, just taking the sword to the Gordian knot and saying, no, get rid of it, build parsers cleanly the way we know in computer science how to build parsers using the correct theory, and then you get rid of the entire class of problems at once. You kill it. You don't just fiddle around with it. And I'll get to other examples over the course of this talk, but a big lesson here, I think, is to think strategically. Don't try to fuss around the edges of a problem. Look for a way to put a wooden stake through the heart of a problem and end it. And the other part here is don't ignore the hardest problems we face because they're too scary. Stare them right in the face and fix them. Start looking for ways to fix whole classes of problems, not fiddle around the edges. LangSec is a really great model. Look at the high level. Don't look at the next bug and the one after that. And so on that note, I'd like to discuss another huge class of bugs out there, one that's been around so long that it's got a gray beard and is getting close to getting Social Security payments, which is type and memory safety violations. That's buffer overflows, use after free, the whole works. Now, as it happens, we already know how to get rid of them. And we've known how to get rid of them forever. If you use a language that doesn't permit type and memory violations, you get rid of the entire problem in one swoop. I mean, it's gone. You might have bugs in your compiler, but if you have a bug in the compiler, you fix that once, and then millions of programs are all fixed at once. So if we were writing our software, all of our software in fully type-safe languages, these problems would not exist. And even if we used Pascal-style languages or Modula 2-style languages, which means the state of the art in the 1970s, a period that I remember, but some of the people in this room weren't born then, if we used techniques we knew 40 years ago, we wouldn't be dealing with this problem. I mean, there are some things around the edges, like Pascal isn't really safe for certain use after free errors. But I mean, for the most part, we could deal with it. But we have a problem. And the problem is that the world runs on billions of lines of C code. And bitter experience says you cannot get rid of all of the errors in C code. Yeah, you can try, but C is just a monster. I mean, the C11 spec has 203 forms of undefined behavior that it describes. All right? You are not, no human being is capable of writing code that does not suffer from some sort of undefined behavior problem somewhere. It's just not something human beings are capable of. And by the way, I love C. I've been writing in C, a large fraction of the time, I think, since around 1984. I mean, I really love the language, but it's kind of like heroin. You have to give it up if you're going to have a reasonable life. And so we have the problem, though, that all of our kernels are written in C, and all of our routers have their software written in C, and all of our media handling libraries are written in C, all of our scripting languages are implemented in C, and we've got this enormous problem. And what do we do? And so we've tried nibbling around the corners. We've done things like we've built static analysis tools. And by the way, I'm not going to slag static analysis tools because they're one of the reasons things aren't worse than they are. But the problem is static analysis tools cannot find all of your holes. And it's just not possible for them to do it. And it turns out that finding 80% of the bugs isn't enough. You need to get 100% of the bugs. And so it would have been better if we'd written everything in Rust to begin with. But it's too late to write all of it in Rust. And we can't stay where we are, because if we stay where we are, we won't fix all of it. So now I'll take like 4 minutes to plug the work that I've been doing for my, my research recently, which is how to bridge this gap. And what I've done is I've created yet another new programming language, and the world really doesn't need another programming language. But the reason I've created this, and it's called CX at the moment because I haven't come up with a better name yet. And the function of CX is to be almost exactly like C except type safe. The language is almost ABI and API compatible with C. There are some things on the edges like var args that I just can't leave exactly the way they were. But it's almost ABI and API compatible with C. The syntax looks almost exactly the same as C's, but it's completely type safe. And what's the notion? The notion is that since it's completely compatible with C, as you're maintaining your existing software source base, if you're doing a lot of work on some file, while you're working on the file, also change it from C to CX. Still links in with the rest of your program. Over a course of years, you know, like Theseus's boat, you replace one piece of the system after another from C to CX. And hopefully, at the end of 5 years or 10 years or 15 years, you've completely replaced the source code base, and you've completely eliminated the type, you know, and the type and memory safety errors. And along the way, hopefully, you've gained some, you've gained some incremental improvement while you've been doing it, because otherwise, there's not a lot of motivation to do it. By the way, I'm lying slightly. There's an unsafe block in CX, because there are places like in the bottom of device drivers or when you're doing a memory allocator where, you know, you've blatted in an Ethernet packet and it's just raw memory, and you have to tell the rest of the system what type it is. And so you need to be able to violate the type system in a few places. But unlike C, where you're always dancing, you know, with a razor-sharp sword, most of the time when you're using this, it's put away, and you only take it out in the very, very rare occasions where you need it. Now, I'm not saying actually that anyone will ever necessarily use my toy, but I think that this approach is a good one. And if it's not my language, maybe it's a cut-down version of Rust or some sort of automated conversion tools or something else. But the point that I'm making is we have to get rid of the C code, and you have to do it incrementally, because you cannot swallow the entire elephant at once. You have to eat the elephant a bite or two at a time. And so regardless of you know, how this gets done, it has to get done, because we have to get rid of all of that C code, and we cannot do it immediately. So this is probably a good time for me to mention 3 of the principles that I'm going to be, you know, covering in the rest of this talk. One of them is that you have to aim for complete fixes. You know, as with the parser problem, as with the buffer overflow problem, et cetera, you won't get there if your ambition is not to completely remove the problem. The ambition always has to be to completely remove the problem. And we know what most of these problems are, and we even know how to completely remove them in most cases, so that has to be what you're thinking of. You're not aiming to leave the problem wounded so it comes back for vengeance in the middle of the night wielding an axe. You're aiming to kill the problem. The second principle, which seems to contradict the first one at the first, but doesn't, is incrementalism. If your fix requires that you rewrite all of the world's software at once, you won't be able to do it. So you need to come up with ways that fix the problem completely, but which can be deployed incrementally. And the third principle, which I think is somewhat less obvious, is this notion that I've named ratcheting, which is that you want fixes that are incapable of backsliding once you have deployed them. And another problem with static analysis and improved testing is that even if you have removed all the bugs from your system, a bug of a class that you already wanted, that you've already removed completely, can creep back in again. You have no assurance that classes of bugs that you've extirpated will not reoccur. And the idea of ratcheting is that you want to use tools that prevent them from coming back. LangSec is interesting because once you've removed your shotgun parser, you know, you've removed a whole set of class of bugs, and they're not going to come back. Moving to type-safe languages provides a kind of ratcheting, because if you move to a type-safe language, there's no way to get a buffer overflow after that, at least assuming that the compiler works correctly. I'm going to argue that formal verification has been misunderstood by most of the community, and it is not a way of achieving perfection. It is a way of achieving a ratchet. Now, if you're my age, you're well aware that formal verification is the technology of the future and always will be. That it's completely impractical, that no one is ever going to formally verify anything of any interesting size, and there's no point in discussing formal verification. It's a pipe dream. And if you learned computer science up till about 15 years ago, this was clear and there was no counter evidence, and you were a fool if you believed otherwise. But it turns out that all of us were fools. Because there have been major, major breakthroughs in formal verification, because luckily a bunch of people didn't listen to the rest of us. And I am so glad that they didn't listen to me, because then they wouldn't have worked on this stuff. And a lot of this has been, part of this has been that people figured out really, really good theory behind how to do formal verification. The Curry-Howard isomorphism, Martin-Luff type theory, the advent of dependently typed systems like Coq, which allow you to express programs and proofs in the same language, and the creation of systems that allow you to engineer large proofs, because it turns out that being able to design large proofs is not a problem, that is any less amenable to systematization than figuring out how to build large programs. These technical breakthroughs have meant that we live in a very different world now. We have a formally verified C compiler that exists called CompCert. And more interesting even than the fact that it's been formally verified, it actually seems to be bug-free. And the two are not necessarily the same thing, and I'll get to that again in a couple of moments. But people have made strong attempts to try to break CompCert using various kinds of basically compiler fuzzing tools that will routinely spit out bugs in GCC and LLVM. And CompCert, there's been one bug found that way, and it's arguably wasn't in CompCert, it was in an include file. We also have a couple of formally verified microkernels. We've got some formally verified cryptographic implementations. We've got a formally verified browser called Quark that I'm going to mention because I think it displays an interesting feature in a minute or two. But until systems like Coq came about, we'd convinced ourselves, I think through a sort of sour grapes argument, that formal verification wouldn't be interesting even if we achieved it. And the sour grapes argument went like this. Well, your formal specification in logic is just another program of sorts, and it can have bugs in it, and it's also going to be large. So what's the point? Even if you could do formal verification, which of course you can't, you'd never be able to produce a spec that actually told you anything interesting. And of course, we've discovered that this isn't true. But I'd like to argue that part of the reason that this isn't true is because it wasn't really understood what formal verification is about. Formal verification is not about producing perfect programs. Formal verification is a ratchet. So, let's say that you know some set of problems that you want to verify in your program. You want to be sure that it has no buffer overflows. You want to be sure that it never goes into an infinite loop, et cetera. And you put out this secure program that you've formally verified, and someone clever comes along and then says, aha, there's a side channel attack that your program is subject to. Nya, 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 nya. Now, if you're just doing testing, well, you try to repair it and you add things to your test cases. But if you're doing formal verification, you add a specification that describes a side channel attack to the set of things that you're proving about the program. You fix the program and prove this property, and you have now ratcheted. That problem will never come back. It's gone. You cannot necessarily know what the full set of things you want to formally verify is. You might never know the full set of things you want to formally verify. But every time you come up with a new one, you fix it, and it's done for good. Unlike, for example, the buffer overflow and testing problem, which we have been suffering for many decades, where no matter how hard we try these half measures, we never get rid of it. If you're using formal verification, if you're using a ratcheting mechanism, you get rid of something, and it is gone. Ratcheting is powerful. I think that ratcheting is one of the things people have to think about hard when they're attempting to come up with new mechanisms that allow us to get past the current crisis. Unfortunately, however, formal verification is still really, really, really hard. Now, it's not too hard to do compared to many of the testing efforts we've got out there. How many of you know about SQLite? It's everyone, basically. How many of you knew that there are about 750 times more lines of tests in the SQLite repository than there are lines of production code? 750 times. There's like on the order of like 100K lines of production code in SQLite, and there are tens of millions of lines of tests. This is kind of remarkable, but it's not that remarkable when you consider that SQLite is another one of these artifacts which may last another 50 or 100 years. Putting the effort in was probably worth it, but the effort required to formally verify something like SQLite is probably not larger than the effort it took to build that test case repository. So it looks like in certain instances this is feasible. But there are still going to be things that are, even so, are just too big to verify. Like, for example, in order to implement a modern web browser, it requires tens of millions of lines of code. And this is just beyond the state of the technology that we've got. So I'll mention now again the Quark formally verified web browser. And wait, haven't I just said you can't do this? How is it that you can do this? So most of you are probably familiar with the architecture in Google's Chrome. And Chrome has the feature that you've got this process that's sort of a supervisor over everything. And all of the renderers, all of the individual web pages are associated with individual processes. And they communicate to the process that runs the whole show. The Quark people took this a step further than that. They formally verified a cage that they put around WebKit. WebKit is tens of millions of lines of C++ code, and not always the best C++ code. You're never going to formally verify that. But they rigged it up so that that C++ code can only talk to the outside world through this formally verified shim. And by making sure that they can only talk to the outside world through this formally verified shim and getting the formal verification on the shim right, they managed to have assurance, theorems that they can prove about the web browser, even though most of the code is kind of crappy. This is interesting. Now, this brings up an old idea, which is containment or isolation, but I'd like to give it a new name, which is software firewalls. Okay, and the reason I like to think of it as that is, you're taking this code that you cannot trust, and you put it behind something that might be relatively small that you can trust, and suddenly you've gained all this assurance that you didn't have before. And I've been thinking about places where this principle can be applied again. And one of the ones that's come to mind in a big way is another one of these things, like the fact that we used to have languages in the 1970s that did things that were memory safe, and we don't now, or, well, we do now. We also used to have all of this work that was being done on microkernels. And multi-server microkernels were actually built partially on this principle, the idea that you have a fleet of processes that implement the contents of what the kernel is doing instead of having a monolithic program. And then you had some way to put a barrier in between failures in portions of the kernel and other portions of the kernel. And in fact, we now have a couple of formally verified microkernels. There's SEL4. There's Certicos, I believe there's another one, and we're getting better and better at figuring out how to build formally verified microkernels. And so, in theory, if you have a formally verified microkernel and you ask the right questions, you prove the correct properties about it, you can build an extremely strong firewall around the large portions of the kernel that you cannot verify, and even protect large portions of the kernel from other large portions of the kernel. So having built a multi-server microkernel like this, you can incrementally improve the parts that you segregated off. You can apply LangSec kind of techniques to the networking stack. You can convert portions of the code into safe languages. You can make progress, and you have, even from the beginning, much higher assurance simply because you have protected the portions of the system from each other. Unfortunately, the problem is this. Writing a new kernel from scratch is really, really hard. It's a lot of work. There's one POSIX-style microkernel out there that actually claims to try to build a multi-server microkernel that executes the POSIX API, which is Minix 3. And Minix 3 doesn't support very much hardware and is kind of terrible in terms of the number of modern features it has. No one is going to rewrite Linux. It's just too hard. So what I propose is that people not try. I propose that one steal it. Um, and so I'm going to bring up some work that's been done by Antti Kanti for his, I'm probably mangling his name. I have a real problem with Finnish double consonants, which are actually significant, except if you're a speaker of English, you can't hear them. But anyway, he created this concept called any kernels or rump kernels. And the idea behind them is pretty straightforward. He started with this desire that he had to debug portions of the NetBSD kernel in userland. But in order to do that, he needed to be able to fake the existence of the entire rest of the kernel to various device drivers or the networking stack or file systems. So he built a library that looks like the rest of the kernel to any of these pieces. And he modified the system so that you can compile any portion of NetBSD either as part of the mono kernel or as part of an independent server that talks to a library that fakes the existence of the rest of the kernel and shims it. And once you've built shims like this for any operating system, and it's relatively straightforward in some places because of necessity, an operating system like Linux has to have a modular interface to file systems because there are many file systems. There needs to be a modular interface to device drivers because there are many device drivers. There needs to be a reasonably modular interface to the networking code. Once you have shimmed that piece of code, you can deceive it into thinking that it's running in a mono kernel and in fact run it as part of a multi-server microkernel. So although it would be difficult to impossible to build a new multi-server microkernel from scratch, you don't have to. We have an open source revolution out there. All of the pieces are sitting on the shelf. The sort of effort would work better, say, if Linus Torvalds would cooperate with having a Linux source that could be built either into a mono kernel or used as pieces in a multi-server microkernel. But even if he did not want to cooperate with it, it would still be possible because the source code is out there. And there are even operating systems like NetBSD that have already been decomposed this way. So it should be possible if we want to actually try to make progress on fundamental pieces of infrastructure like operating system kernels, to apply all of these techniques that we've talked about and actually get ourselves from a situation where we have very poor assurance to a situation where we have very good assurance. And as long as we're discussing operating systems, I'd like to make another pitch here, which is for capability-based systems. And the problem with capability-based systems is, again, it's the same as everything else. We've all known for a long time that capability-based systems are the systems of the future and always will be the systems of the future. And there have been a couple of exceptions. You know, there's been KeyCOS and other things like that. And there have been some experimental ones like Eros that have not been too bad. But you know, for the most part, we have not actually used capability-based systems out there, even though it's pretty clear that capability-based systems are the best way to cage application code and to keep application code from being able to talk to other application code or the kernel in ways that we don't want it to. But how do you deal with that? And you know, you're not going to build an entire operating system from scratch successfully these days. You're not going to build an entire set of applications you know, for a new API from scratch and get anywhere. So for those who aren't aware of it, Robert Watson at Cambridge and his collaborators have come up with an interesting solution to this, which is the hybrid capability model. And they have such a thing called Capsicum. And Capsicum basically works like this. It's in the FreeBSD kernel, and there's a set of patches for Linux that implement it. And your application, at some point early on while it's starting, runs a system call that says, I will now move into capability mode. And once you've moved into capability mode, you are there for good. There's no system call to get you out of capability mode. And once you're in capability mode, you're very caged. You can only touch things that you have capabilities for. Capabilities in the Capsicum world are file descriptors. And in tests, it looks pretty good. They've been able to cage lots of software, even Google Chrome. You know, there's normally some sandbox code that exists for Chrome on a number of operating systems. The sandbox code that uses Capsicum is a fraction of the size, a very small fraction of the size of the sandbox code that's required on other operating systems. And so I think this is actually kind of a cool thing. So there were a lot of other things that I wanted to cover today, like ways to improve our network protocols, strategies for repairing big problems in application security, including the use of capabilities, et cetera. But I don't have time to go over it all, and I don't think I need to go over it all. I think the important thing here is that there's an overall pattern, and the pattern is worth looking at. We've got all of these interesting tools and advances out there, and we often know that they are really good advances. Capability systems, we understand why they are superior. We understand why using a language that does not have, that's type safe is better than using a non-type safe language, and a language that's memory safe is better than one that's not memory safe. We understand now why you don't want to build parsers in a half-assed way. None of them individually is sufficient to fix things out there, but most successful engineering, in most fields I would argue, is combinations of systematic approaches and hard-fought lessons that have been learned over decades. And computer science is finally approaching the point where we may be able to combine the lessons we've learned into an actual engineering discipline. And I'd like to remind everyone of some of the things I've gone over today, which is, first of all, that our infrastructure is not actually turning over so rapidly that we cannot take the time to address these things. It's been around for decades. It will last for decades more. It might last for more than decades more. It will certainly live long enough that long-term efforts to fix it are worthwhile. The second thing is think strategic. Think about full fixes, not remediations, not tactical fixes, not half patches, not ways to deal with individual bugs. All of those are necessary, of course, but they're not the way to fix things long term. They're just a way to get some improvement for the moment. You need to think strategically, not tactically. If you know there's a full fix for a problem, go for the full fix. And in many cases, we know what the full fixes are. We've just been scared to go after them. We have to quit being afraid of that sort of thing. If you strike at the root of the problem, it goes away. If you don't, bitter experience says that it will never go away. All right. On the flip side, when you do completely fix problems, we have strong evidence that they vanish, and they just go away, and they cease to be things that people think about at all. The third thing is incrementalism works well, provided you apply it towards fully fixing problems. You can't throw away billions of lines of legacy code, but you can probably fix them incrementally, bit by bit, and so you probably should. The fourth thing today is formal methods are now a real thing. They provide actual assurance, which is valuable. They're expensive, so you can't use them for everything, but you can certainly almost always use them to cage portions of your code that you cannot verify. And they act as ratchets, and ratchets are a thing that goes beyond formal verification. They cover several of the things I've talked about today. Using ratchets is necessary because testing, testing is good, testing is important. You can't write code without testing, but it will not assure that you don't backslide, whereas techniques that provide ratchets keep you from backsliding. So if you have ratchets, you may never be able to get to perfection, but you can asymptotically approach it. You can get as close to it as the set of problems that you know that you need to fix are. Sixth, containment and isolation is a really, really, really powerful technique. Things like formally verifying a cage around your browser, formally verifying a microkernel, adding a capability system to your operating system so that you can cage applications better. If you cannot keep a bug from spreading, find a way to cage it, and you can combine that with things like formal methods in order to assure that the cage is really, really, really strong. And lastly, I'd like to suggest that it is time for focused projects that produce really, really reliable infrastructure on which we can build the rest of this stuff, which is part of the reason I was mentioning things like the possibility of actually producing a microkernel that we can use in things like our phones and our routers and what have you that doesn't suck. Open source has changed the picture here. Formal methods have changed the picture here. Understanding how to deal with a lot of the fundamental problems have changed the picture here. But we should be in a position now to take pieces we already have without having to throw the things we have away and convert them into infrastructure that is built on bedrock instead of being built on sand. And I think whether we need to be bold about this. We should think about how to combine the techniques that I've been talking about today to create well-engineered infrastructure, and we need to do that starting now if we want it to actually be there in 10 or 15 or 20 years, because we will still need it in 10 or 15 or 20 years. And I think that we have strong motivation to do this, because if things keep going the way that they've been going, and you simply have to pay attention to the news to be aware of that, at some point, a lot of us are going to be in trouble when our civilization vanishes out from under us, along with a lot of our computer infrastructure. And I, for one, am too old to take up subsistence farming. I'm simply not going to survive that way. So I hope that rather than taking up subsistence farming, what we take on is the challenge of trying to fix our infrastructure security instead. All right. And I have, I think, about 10 minutes for questions. Yes? Well, I think it usually goes in the other direction. I think that in most disciplines, first the engineering gets figured out, because you first have to know what it is that you want to ask people to do consistently before you can ask them to do it consistently. And you need to have examples of things that are done correctly before you can tell people to do them the way that the correctly done examples are, rather than the incorrectly done examples. I think that the problem at the moment is getting ourselves to the point where we even can consistently say, these are examples of operating systems, networking stacks, web browsers, web servers, application stacks that actually work well. And at that point, it might be possible to tell people that they're being unprofessional if they're not following those kinds of examples. But until we're at the point, I think, where we actually have some infrastructure that we can point at that's actually good, I think it's a little premature to be telling people this is the best way to do stuff. At least that's my opinion. Other people may have different opinions. I think you were first.
So the idea was to come up, and these devices have all sorts of, there are all sorts of horror stories about bad things happening with them. So the idea was to come up with a set of good practices that at first would be voluntary, but just like the building code for fire safety and water safety and stuff like that, eventually it would become so obvious that you should be doing this that it would get enacted in law. But the baby step was to first identify what's a good practice if you're putting together medically. So people are starting to think about that. Yeah. There are some baby steps in that direction.
By the way, I will note that medical devices are one of the few places where the term remote execution vulnerability actually means what it says. The problem One problem there is we have to be a little careful, I think, about regulating the wrong things. For example, one of the reasons why lots of medical devices in the US that are sold by large companies still have Windows XP running in them is because the device is approved as a whole, including its software package. And even though the device as shipped is horribly vulnerable, or the device as it is in the field is horribly vulnerable, it is easier. We've made it easier to leave it vulnerable than to deal with the burden of getting it reapproved. So we have to actually be thinking about not asking people to do the wrong things or giving them perverse incentives.
Just on that point, I spoke with people at the FDA, and that is that these people that as an urban legend. They say that it's used as an excuse that they have very lightweight, fast-track processes, specifically to allow these kinds of things. Even though this concept of it's a gigantic mountain you have to climb, you make even the slightest change. It's just
Well, you may know more about that than I do. Yes, in the corner.
So, I like your talk. Have two questions, high level and low level questions, both about your better version of C. The low level version is Jonathan Shapiro at BitC.
Yes.
Same thing.
Also shares a doctoral advisor with me, but.
Okay. And second is how that fits into the high level part is how it fits into containerization, et cetera.
So Jonathan's work on BitC is not, so I want to say that CX is not a good language. BitC is designed to be a good language for implementing low-level operating system work. It's designed to be something that you would want to actively adopt for a fresh design. The function of CX is very, very different. And anyone who works day-to-day in C knows that it's a bit of a pain in the neck. You have to do lots of stuff from scratch that other languages give you lots of infrastructure for. But the function of CX is not to fix any of that. It's to look so much like C that you can just slip it in without terribly much effort into existing code. And so BitC has a different function to it. Rust, by the way, is probably a much better language if you're trying to build something from scratch than my stuff would ever be, assuming my stuff really sees the light of day. But my stuff isn't designed to help you build stuff from scratch. My stuff is designed purely to try to fix the installed base. So does that kind of answer your question about where the two things fit together?
Yeah.
Okay, cool. Yes?
So I really, really like the conceptual model of ratchets, and it's a really awesome pattern that you've hit on because you're right. You know, these are ways to move forward and never move back. So what I'm wondering is, having recognized this pattern in a few occasions, how do we recognize it more and more quickly?
Well, I think that part of that is, and I don't care if anyone attributes the name to me or what have you, but I'd like people to start spreading the idea of ratcheting and why ratcheting is good around. And I think that as people think about it more, the examples will come up. In general, though, just keep in mind the notion of any sort of change that you make where it is impossible for the problem that you have just fixed to backslide so long as the mechanisms remain in place. So long as you maintain the proof, even as you change the code, the things that you proved will not cease to be true. So long as so long as you don't introduce assembly statements or code that's linked in from C libraries into your Rust code, the Rust code will remain immune to various kinds of type anomalies, et cetera. So, but if there's one thing actually, if there's one of the couple of ideas that I would like people to stick with people, it's the idea of ratchets. And the idea, by the way, that formal verification is valuable not because it provides perfection, not protection, but because it provides ratchets. Yes? Well, there are lots of them in the real world. Every time someone builds a system that lives inside of a container, containers are actually poor cages, but they're thought of as cages. When people build, so the only formally verified cage I am aware of is Quark. Quark was presented at Usenix Security a few years ago. The paper is very good and very readable. The web browser itself is kind of clunky. The web pages themselves are fine, but the toolbar at the top is pure text because they had to formally verify the I/O for it. And Quark is just is an academic toy, but that's probably the first and best example that I can think of in the academic literature of building a formally verified cage, and I recommend looking at that. Yes.
Could you comment a little bit about what you believe are the essential hardware features to support the software? In other words, the hardware community is apparently they're developing all kinds of security fixes and additional things for the ISA. But what are the things that we really have to have in order to get where your mission is?
I don't know what we have to have, but I can describe some things that I think are useful. They're the obvious things, for example, like virtual memory, which everything has now. So that's not an interesting feature. I think that in order to have really good performance in microkernels, I think that getting context switch times down will probably be a valuable aid in doing that. And I think there are things that the hardware people can do. One of the problems that we have in a lot of the systems we've got these days is the hardware is designed against the benchmarking against existing software. So if existing software doesn't try to do something, like doesn't try to do huge numbers of context switches in the course of doing some systems code, the processors don't support it very well. But that doesn't mean that they couldn't. It means that they currently don't. I'll mention something that's not connected to any of the things I've discussed today, which is I think that hardware read and write barriers to make garbage collection performance much higher are probably a thing that's quite simple to do in hardware. It's relatively difficult and expensive to do some of that stuff in pure software. And being able to use for applications, not necessarily for kernels, where you get a lot of your performance by being very careful about your memory allocation. But for applications, being able to switch to very high performance garbage collected languages will probably be a significant win. And so some support for that is probably of use. Another thing that I think is actually quite useful. Most modern processors, because no one has actually been bothering checking for integer overflow much, most of them don't have very good support for checking for integer overflow and similar issues. And it turns out that integer overflow is a real problem. We all think about memory safety as being the problem in type safety. It's not the only problem. Integer safety is really important. Hardware support for integer safety is probably a big deal. And there are a few other things that I can probably come up with, if I spend a couple of minutes thinking about it. But I think that until the software actually starts demanding these features of the hardware, until it gets to the point where it's obviously performance critical, I'm not sure that the hardware vendors will really see that they need this stuff. Oh, and by the way, one other thing. I mentioned Robert Watson's group at Cambridge. They now have a capability-based microprocessor that they built. And it actually will run FreeBSD, which I find kind of fascinating. And it's basically some additions that were made to an open source MIPS design, but the same principles could be used on other things that might actually have some significant benefits. But in general, though, I think the real issue at this point is getting the software to the point where it's obvious that it demands the features from the hardware. We're so far behind on making the software secure that arguably, the hardware vendors will not feel much pressure to fix many of these things. Yes.
So following on from that, it seems to me that the difficulty of scaling works a lot might work to our advantage in the sense that if we end up with a lot more cores, I'm thinking mostly of the big little design paradigm that ARM has adopted. If we can sort of dedicate a core to a particular component of microkernel, that might encourage the development of microkernel.
Oh yeah, because it's an easy way to decompose your microkernel. If you've got huge numbers of cores, you don't have to worry about the context switching, but you do need a way to pass messages between them efficiently. But that may, in fact, be something. that we get out of it. By the way, I do want to point out that Moore's law hasn't topped out. What's topped out is clock rates. We're going to start building processors that are going to scale into the third dimension. And we can go very, very far, even without shrinking individual components, before we actually hit the point where we stop doubling transistors. And Moore's law is technically about the transistor count. But the fact that we have run out of clock means that we are building that we're going to go to intense numbers of cores. And if you've got 50,000 cores in a machine, yes, microkernel architecture may benefit dramatically from that sort of shift.
It's just that, I mean, that feeds into the question of what the hardware folks do.
Yes.
Make a message passing back.
That's a possibility. All right, any others? Yes, and I think this may have to be the last one because I think I don't want to take away time from someone who's actually got something to present rather than me. Yes.
So we have a very short question. What's your opinion on language like D, for example?
D?
Yes.
I don't really know much about D, so I don't have much of an opinion on it. I know a lot about Rust and Cyclone and dozens of other things. D, sorry. Okay.
Maybe I could modify this. What do you think of non-Turing complete languages?
Non-Turing complete languages. Well, Coq is a non-Turing complete language, but you can specify the operation of Turing complete programs that you extract from it. In fact, and so it's perfectly useful. Whether there are uses for non-Turing complete languages in building secure systems, there may be. I haven't read a lot of that literature, so I don't have a good answer there.
We'll have some later talks on the subject.
Well, and then so I will be learning along with other people in the audience. Okay.
As time goes, at this point, we're really just needing the coffee break. So,
Well, if people have more questions, I'm happy to answer them. But I think that the hands were starting to peter out anyway. Anyone else? Okay. Well, thank you so much for inviting me.